Okay, welcome back, everybody. So, in today's lecture, I'm going to talk about some practicalities in parallel computing, and essentially, I'm going to talk about design and evaluation of parallel programs. And this is the outline for today's lecture. So, first, I discuss a taxonomy of parallel machines, because if you want to know how to design a parallel program or how to evaluate that program, you need to know on what machine you are performing the computations on. And then we talk about parallel metrics, which are the metrics that you want to use to measure the performance. And then we talk about parallel prediction, which provides a theoretical framework for you to evaluate your performance, your performance of to evaluate the performance of your program without implementing that. And finally, we talk about design patterns and how we can start the design process to write parallel programs. All right. So let's first talk about the taxonomy of the parallel machines, which is called Flynn's taxonomy. And this taxonomy basically introduced by Michael Flynn in 1966 for general computer architecture. And it classifies the machines, the computers, based on two different things. The first thing is how many data items the machines can process concurrently and how many different instructions they can execute at the same time. So based on these criteria, we can come up with four categories: single instruction, single data machines, or SISD; single instruction, multiple data, or SIMD machines; multiple instruction, single data, or MISD machines; and finally, multiple instruction and multiple data, or MIMD machines. So let's see how each one of these machines work based on this Flynn's taxonomy. So first, let's talk about single instruction and single data machine, or SISD. So basically, it is a traditional computer system in which you have a data pool where your data lies in, and the instruction pool where you have your instructions. And finally, you have a PU, or a processing unit, that fetches the data from this data pool and fetches an instruction from the instruction pool, and then performs a computation on the data using this instruction. So this is a traditional machine. And in this case, this machine can only execute one instruction at a time, and it can also operate only on a single data item. So that's why it's called single instruction, single data machine. However, most of the currently available machines do not belong to this category, because now we are in the era of multi-core machines. But in a multi-core machine, we still can have this SysD machine, but in each core. For example, you can write very simple sequential programs using this uh, SysD machine. So it's kind of traditional, and it is quite old architecture. All right. So the next one is single instruction multiple data, or SIMD, which is one of the most widely used machines today. So in this case, you will still have a data pool and you have an instruction pool, but you have multiple processing units. And each processing unit will fetch a data item from a data pool, right? Simultaneously with other processing units. And then a single instruction, which is called a vector instruction, is fetched from this instruction pool. And then these data items that are fetched from this data pool are processed simultaneously and at the same time, right? So in these SIMD machines, the same instruction is simultaneously applied on a collection of data items, not only on a single data item. So here the question is, for what kind of parallel applications this SIMD machine is going to be useful? So anyone knows anything about that? So what kind of parallelism fits this kind of uh, SIMD machines. Any ideas? So if you look carefully, you see that we can process different data items, right? But with a single instruction. So it means we can perform data parallel algorithms. So we can implement and design data parallel algorithms where you split the data, send it to different processors, and then you perform the same computations on that, right? Which is quite perfect when you have GPUs, and GPUs basically perform this single instruction, multiple data operations, or as NVIDIA calls it, single instruction, multiple threads, where you have a single instruction and you perform it and you use it on different threads, right? So GPUs are SIMD machines, but at the streaming multiprocessor level, which we are going to talk about in the next lecture. But just to let you know that I just wanted to let you know that these are SIMD machines. Okay, and some examples can be image processing and data processing. So for example, in image processing, you want to apply a function to each pixel in the image. So that's why it fits well to this um, SIMD architecture. Okay. All right. So the next one is multiple instruction, single data or MISD machines, which is rarely used in practice, but you can think of it as a fault tolerant system where you want to apply multiple algorithms on the same data for verification purposes. So in this case, we have a data pool here and an instruction pool here, but we have two processing units. Each processing unit fetches different instruction from this instruction pool, but they only work on a single data item. So basically, the data is processed by multiple machines. For example, they can apply multiple algorithms on the same data. So this is not the architecture that we're going to use in this class. And finally, we have multiple instruction and multiple data machines, or MIMD. So these are general purpose computers which contain different processing units, and each processing units can fetch different instructions from the instruction pool and also can fetch different data items from the data pool, right? And so they can perform different kind of computations on different kind of data sets. So these computers are basically suitable for both data parallel and task parallelism. So you can perform both data parallelism and task parallelism, but it's up to the programmer how to divide the tasks on these machines. So now I have a question for you. So how can we use this MIMD machine for data parallel tasks? Because for task parallelism, it's kind of simple. So you have different tasks, and then you deploy each task to each processing unit, right? So how we can use this architecture for data parallel algorithms? So any ideas? So it's quite simple because in this case, we can assign only one task to each processing unit, but each processing unit will use different data, right? So we don't need to use different tasks for different processing units. So in this case, if we want to perform a data parallel computation, we just need to have a single task to be run by each processor. All right. So these are the most versatile category of machines, and they can include multi-core systems, computer clusters, even GPU machines that we are going to talk about in the next lectures. So in this case, each core uh, also can have a SIMD machine inside. So basically, when you have these MIMD systems, you have multiple processing units, and each processing unit itself can be a SIMD machine. So then you can have a hierarchical parallelism that you can use in your programs. So this kind of architecture can be used for general purpose parallel computing, like web servers, numerical simulations, and also other similar things. All right. Any questions about these four types of machines? By the way, can you hear me? Nobody says anything.
Yeah, we can still hear you.
Okay, good. All right. So this Flynn's taxonomy actually got extended during time, and you can further categorize these MIMD machines into shared memory systems and distributed memory systems that we have talked about already. And you can also uh, categorize shared memory systems as well based on two other categories. The first one is master worker shared memory systems, and the other one is symmetric multiprocessing platforms or SMPs. So let's briefly see what are these two shared memory architectures. So in symmetric multiprocessing platforms or SMPs, you basically have different cores, but they are kind of identical, like in terms of their characteristics, right? So these are just general purpose CPUs that you have on your desktop or on your laptops. And by the way, the master worker shared memory systems, as the name suggests, has a master processor and some worker processors. The master processor is a general purpose processor, and it is responsible for running the operating system, for example, performing some I/O operations. But the worker processor, uh, which is which are also called co-processors, they are responsible for running a specific piece of software, right? A quite famous example in this master worker shared memory system is a PlayStation 3 Cell BE processor, which you can see it's schematic here. So it basically has two types of processor, the master processor and the uh, co-processor or worker processor. So here the PPE, which stands for power processing element, is a is the master processor, which is responsible for running the OS and managing the co-processors. And SPEs, which stand for synergetic processing elements, these are uh, worker processors. And in this case, in this architecture, this PPE is a general purpose CPU, but these SPEs, they are SIMD machines, 128-bit SIMD machines with their local storage, and they can use this shared memory using this memory controller, right? So we have a master processor and some worker processors with their local storage, and they can access the same memory space. So this is how this Cell BE processor looks like. All right. So having said that, an important question comes uh, into picture, which is, can heterogeneous systems, including the systems which uh, have both CPUs and GPUs, be considered as a master worker shared memory machines? So the question is, assume you have a system which has a CPU and a couple of GPUs or even one GPU. So is it considered as a master worker shared memory machine? So anyone can say anything about that? So if
W-
you,
I
yep.
would think it is.
Oh, well, in the shared memory machines, the memory is shared, right, between the different processors. But In this kind of architecture, when you have a CPU and different GPUs, the system's memory or the CPU's memory is physically different than the GPU memory, right? So although they can be installed on the same machine, but their memory is not shared physically, right? So in this case, CPU and GPU, in the case of a machine with CPU and GPU, you don't have a shared memory system. So then you cannot really define this master worker shared memory machine. So it's a distributed memory paradigm. So this is a tricky point about this master worker. So in this case, you need to have your memory to be shared between the different processors, even they can be heterogeneous processors. So in this case, this architecture that I'm showing here is a distributed memory architecture. Okay. All right. So modern shared memory parallel machines, they usually have two important features. They have increased the core count combined with SIMD instructions. So they have multiple cores, and each core has SIMD instructions in it. And they also have combined heterogeneous cores in the same package, like these APUs or accelerated processing units that you can see in PlayStation 4, 5, and Xbox One, which has both CPU and GPU on the same chip. So this is a master worker. The APUs are master worker shared memory systems. All right. So now we know a little bit about the categorization of parallel machines. Now it kind of makes sense if we can evaluate the performance of our parallel programs executed on these machines. So this part is going to be a little bit theoretical. So, and let's see how we can define some performance metrics to measure the performance. So before measuring the actual performance, we need to have some metrics to be able to measure that. So let's see. So now I would like to have a discussion with you about this. So the first question is, why do you think measuring performance in a parallel system is important? Why we actually want to measure performance? Anyone has any ideas about that?
I think to assess the architecture of our system
Okay.
on paper.
Yeah, but what is the goal, the final goal of a parallel, all of these problems? So you have parallel architecture, parallel algorithm, parallel programs. What's the main goal? What we want to what we want to measure?
How well our program have been parallelized.
Yes, and also the speed, right? So the first thing is we want to evaluate the effectiveness of our algorithm or program. We want to know how fast uh, we are in solving a problem using a parallel program. And then we want to know and identify the bottlenecks. So what are the bottlenecks of this like program and how we can optimize resource utilization. So we can define some key metrics for measuring these things. So we can define three important metrics. The first metric is a speed up, which answers this question that how much faster is the parallel execution. Then we can define efficiency, which means how well we are using the hardware resources in our system. And finally, we can define a metric for scalability. So how does performance change with more resources or problem size? So these are the key metrics that we want to talk about in this part of the lecture. And the main goal here is to kind of quantify the performance of parallel system. Okay. So the first metric is the speed up. So speed up, as the name suggests, measures how fast how much faster a parallel program runs compared to a sequential program. So we want to know if how much we are doing better using a parallel program. So the equation is quite simple. So we just need to divide the times taken by the sequential program by the times taken by the parallel program, right? So quite simple. And here both times, the sequential time and the parallel time are wall clock times, as we discussed it before. So here there's an important question about the speed up, which is what is the ideal speed up if we use n processors? So assume we are using n processor. So ideally, how much speed up we really want to have if we use n processors? Anyone has any idea? So assume the sequential time is 10 seconds and you are using 10, uh, 10 cores, right? Or 10 processors. So what would be the ideal speed up in this case? What you really want to have when you are using 10 cores for a problem that takes 10 seconds?
It should be n.
Yes. So in this case, you just want your speed up to be n, right? So if everything is perfect, you want to divide the workload based on these n processors equally to divide the sequential time by the number of cores. All right, so let's see if we can get that. So the problem with this speed up formula that I wrote here is that it can be influenced by a lot of things, like the programmer's skills that implemented that code, the compiler. If you use GNU compiler or if you use Intel C++ compiler, you can get different wall clock times. Then it also depends on the compiler switches. If you use compiler optimization, for example, it also depends on the operating system, the file system of the operating system, and even time of the day. Because, for example, you want to execute your algorithm on a data center, and that data center has different workload depending on the time of the day. So then you can have different speed of results. So to avoid these issues, we need to satisfy two requirements when you want to report speedups. So the first thing is your programs, the sequential one and the parallel one, they should be tested on identical software and hardware platforms. So you should, for example, use the same compiler switches, the same operating system, and also the same hardware that you test your program on, and also under similar conditions, right? And the second requirement, which is important, is when you want to compare your parallel program with a sequential program, you have to make sure that the sequential program that you are comparing against is the fastest one, that you have available, right? So these are two requirements that you need to know when you want to measure the speed up of your programs. And you can also satisfy these requirements when you are working with your project or with your assignments. All right. So the speed up can tell us if it is feasible to accelerate the solution of a problem. So for example, if a speed up is greater than 1, we know that with this parallel like algorithm, we can have some benefits. But unfortunately, it doesn't provide any information if the parallelism is done efficiently, if we used the resources that we had effectively. So if you have 2 times the speed up, but instead of 1 core, you are using thousands of cores, so probably it's not, your algorithm is parallel, but probably it's not efficient. So, and for that, we define another metric, which is called efficiency of the parallel program. And it's quite a simple equation. You just need to divide the speed up by the number of processors. And then if you simplify and substitute the speed up equation here, you can get this the serial time divided by n times parallel time, right? And here n is the number of CPUs or cores. So this equation gives you the efficiency of your algorithm. And roughly speaking, it measures the average percentage of time that a CPU is utilized during the parallel execution. So it tells you how much of your CPU is utilized during the execution. So for example, here, assume we have a system with n processors, and here the sequential time is 100 seconds, and the parallel time is 25 seconds, right? So if you compute the efficiency, you see that the efficiency in this case is 40% or 0.4, which means our CPUs only utilized 40% of the time for active computations, and they were idle for 60% of the execution time, right? So in this case, the efficiency of our program is 40%. All right, so now I have a question for you. So in this case, as I mentioned, we have 40% of active computation and 60% of being idle, right? So what is the situation that our CPUs will be, in which situation our CPUs will be idle? So what's happening in our code or in our program that makes the CPUs to be idle? Why they are idle in a typical program? What do you think? When I say they are idle, it means that probably they are waiting for something, right? So in a typical parallel program, why different CPUs or different threads are waiting for something?
Because of data dependency on the other.
Yeah, this is one reason. Probably they want to do some I/O operation, right? Because when they have data dependency, they want to get data from each other. They want to have synchronization. They want to have coordination. Probably they have some race condition that they want to handle, right? They want to manage shared resources. So that's why your program, your efficiency might be low when you have when you have in your parallel programs. But let's see what efficiency of 100%, what it means. So it is really rare to have 100% of efficiency, but let's see what it means. So the first thing that it means, it is that the speed up is n in this case, because if the efficiency is 1, well, it means that the speed up is n, right? So we have the ideal speed up that we talked earlier a little bit. It also means that the workload is equally divided between the n processors, because in this case, when the efficiency is 100%, it means that all processors, they are starting solving their task at the same time and they finish at the same time, which means that everything is perfectly divided to the processors. And another interpretation is your processors utilize the 100% of the time, and they are never idle during the execution. So in this case, if our speed up is n and we are in the ideal speed up, we call this program, this parallel program, with linear speed up. So in this case, the parallel program exhibits a linear speed up, which means your speed up is increasing linearly as you add more cores into your machine. However, in reality, the speed up is usually smaller than n because, as I mentioned, the processors need to spend some time on coordination, synchronization, handling shared resources, that race condition handling, the mutex locks, and these kind of things. So with with the knowledge of a speed up and efficiency, you can draw some curves that are called a speed up and efficiency curves. So, for example, this is the speed up curve, the one in the left, for a numerical integration algorithm. And as you can see, as we increase the number of threads because of the parallel overhead, the speed up is not linearly increased. And this blue dash, the dash blue line is our ideal speed up. So then when you have this ideal speed up, you can also compare how well your program is behaving. And then when you have the efficiency also drops when you add more threads or more cores into your machines, right? So in your homework assignments and your especially your projects, you need to report these efficiency and speed up curves to let the reader know how efficient your parallel program is. So these are important curves that you need to consider when you have an implementation. All right, so some important notes about the speed up and efficiency. So when you want to measure the performance for the speed up and for the efficiency, you should always use your hardware threads. So do not create more than your number of your hardware threads, right? So because we want to be perfectly matched, we want to perfectly match the number of threads in the program and the number of hardware threads. Otherwise, you are creating even more overhead to creating new threads by the operating system, which takes a lot of time. And another thing, another note is that you can use the ideal speedup to, as I mentioned, to measure how well your program is. And keep in mind that the efficiency is the measure of resource utilization. So if you have a good efficiency, which it means you are using your hardware quite effectively. And if you didn't get a good efficiency, if your efficiency is low, it means you didn't have a good design in your program, so you didn't design it very well, or at least your design can be improved. So the efficiency is the sign of poor design. So you can judge your design decisions based on the efficiency of the of your algorithm. Okay. All right. So another question that we need to ask, now we know the speed up and we know the efficiency, but we want to know how a parallel algorithm behaves if you increase the computational resource or the problem size or both together. So basically we want to know if the program scales with the problem size or the computational resources. And this can be seen through scalability. So the first scalability criteria is called weak scaling efficiency. In the weak scaling efficiency, what you do is the following. You increase the problem size proportional to the number of processors, right? And then you compute it using this equation. So the weak scaling efficiency is the time taken by the sequential program divided by the time taken by the parallel program. However, the parallel time here is the time to solve a problem that is n times bigger than the sequential one. So then you can have this weak scaling efficiency, and it is a function of number of processors or capital N, right? So the takeaway point here is that the problem size grows with the number of processors. So they are proportional to each other. Another type of scaling is a strong scaling efficiency, in which you fix the problem size and you want to know how your algorithm scales as you add more processors. And the equation is the same as the efficiency, right? You just need to divide the sequential time by the number of cores times number of the parallel time. So in this case, we call a program to be strongly scalable if when we increase the number of processors, we can keep the efficiency fixed without increasing the problem size, right? So if we have fixed the problem size, and if we add more cores to our program and we see that the efficiency is fixed, then we say that our program is strongly scalable. But the situation for the weak scalability is a little bit different that I'm trying to explain it in just a slide. So according to the definition, a program is called weakly scalable if the problem size can be increased proportionally with the number of processors. So if you increase the problem size as you increase the number of processors, and then you can keep the constant efficiency, right? So let's see an example. So in this case, suppose the sequential time is n, and n is the problem size. So for example, if your problem size is 10, like a vector of 10 elements, then it takes like 10 seconds for our program to process that, right? And the parallel time is the problem size divided by the number of cores plus one, right? So assume we have a parallel algorithm that needs that amount of work for processing n elements, okay? So the question is, uh, can we find a factor x that we need to use to increase the problem size, right? If we increase the number of cores by the factor of k. So roughly speaking, we want to know how much we can increase our problem size if we increase the number of cores to keep the efficiency constant. And it is easy to compute. So we can compute the efficiency using the efficiency uh, equation. So the time taken by the sequential program divided by the number of cores times the time taken by the parallel program, right? If you simplify, this is your efficiency. Let me try to highlight it. So if you do that, this is the efficiency of your original sequential program. So we want to know if I increase n by the factor of x, if I scale n by the factor of x, and if I scale the number of cores by the factor of k, can I find x that satisfy this equation? So if you solve it, you can see that if x is equal k, you can substitute it in the equation. And finally, for the parallel program, you can get this efficiency. For the scaled program, sorry, you can get the same efficiency as this efficiency. So in this case, we know that if we increase the problem size that we did using this xn at the same rate that we increased the number of processors here using this kn, because the efficiency is unchanged and fixed, we know that our program is scalable. And in this case, we call it weakly scalable because we are also changing the problem size, not necessarily the number of cores. Okay. So any questions about weak and strong scalability? Right. Okay, so now that we know about performance metrics, which were speed up, efficiency, and scalability, we can now theoretically predict the performance of parallel programs. But let's see why we actually want to predict performance. Why not just implementing a parallel program and just measure the speed up and efficiency and scalability? So we want to know the motivation. So let me ask you this question now. Why we would like to be able to predict the performance of a parallel program without implementing that? So why we really want to do that? What's the benefit?
We probably want to know if it's viable to do the parallelism before we start it.
Yeah, but why we don't just implement the parallel program and then measure the performance? why we want to predict it even theoretically or with some approximations to know that beforehand.
I think because coding it just for tests is going to be costly.
Yes. So that's relatively correct answer because generally speaking, parallel programming is hard. So it's quite challenging if you write a parallel program from scratch, right? And then see if it works or not, or if you have a speed up or not. So that's why we need to have some sort of at least rough prediction about the efficiency and the speed up of the program. And the challenges of writing a parallel program are, for example, the thread and process coordination, because they need to have synchronization. We need to be really careful about load balancing, which means dividing the workload equally to the threads or processors. Then problem decomposition is also not as straightforward in a lot of applications. So you should be really careful with how you decompose your problem into some independent tasks. And finally, when it comes to designing algorithms, it's kind of not as straightforward to terminate an algorithm when you have different threads working on the same problem. So these are some challenges of parallel programs. And because of that, development of parallel algorithms are costly. So that's why we want to kind of understand how our algorithm or our parallel algorithm will behave if we implement that, at least with some rough theoretical framework. So based on that, parallel programming should be used only for applications that can benefit from it by providing faster solutions. So the, the whole uh, the whole reason here is to know if it is worth it to implement a parallel program for a sequential program. So it should, if it is worth it, then we do that. Otherwise, we should consider other options. And to understand that and to predict the performance, we need to have some ideas about the serial implementation of that algorithm. So if we have a serial implementation, which is usually easier than the parallel implementation of an algorithm, we can use that serial implementation to theoretically predict the performance of the parallel program. And this is what exactly we want to do in this part of the lecture. So the first prediction framework that we would like to talk about is called Amdahl's law, which is an approximate mathematical model for performance predictions of the parallel programs proposed by Amdahl. So this law considers some assumptions, and based on these assumptions, it gives us a prediction for the speedup. The first thing that it assumes is that there exists a sequential program with the execution time of t. So it assumes that we have a sequential program at hand, and the execution time of that sequential program is t, right? The next assumption is uh, we consider a number alpha, which is between 0 and 1, and we say alpha portion of the program can be parallelized. So for example, if alpha is 60, is 0.6, we know that 60% of our program can be parallelized. And 1 minus alpha, in my example, 0.4, must be done sequentially. So alpha portion of the program can be parallelized, and 1 minus alpha portion of the program must be done actually sequentially, right? And in this law, we do not assume to have communication overhead and everything is perfect, right? So these are the main assumptions considered by Amdahl's law. So now, using this assumption, we can compute the speedup of our program. So remember the speed up equation, the time taken by the sequential program divided by the parallel time. In this case, according to the assumption, the time taken by the sequential program is t, and we should just compute the parallel time for this program. So let's see how we can compute the parallel time. So we know that 1 minus alpha portion of the time is used for the serial code. So this is the serial part of the parallel execution. And then the alpha portion we can parallelize, right? So in this case, we just need to divide t by n, the number of cores, times by this alpha portion. And if we simplify, we get this equation for the speed up according to this Amdahl's law. So this equation is quite important in parallel computing because it tells us the speed up is kind of related to the number of cores and to the portion of your program that can be done in parallel. Only these two parameters. But to know the maximum speed up, we just need to uh, uh, take the limit of this capital N to go to infinity. So if the number of cores goes to infinity, and if we compute the limit, the speed up, the maximum speed up in this case, can be obtained by this equation, which is one of the most equations in parallel computing, which tells us that the speed up of your program it is actually limited by the serial portion of your algorithm, right? So, for example, in this figure, I'm showing you the speed up curve and the efficiency curve, depending on different alpha. So, for example, if 95% of your algorithm is parallelizable, your speed up will be smaller than 10. Your maximum speed up would be kind of upper bounded by this number, right? So even your program has 95% of parallelization capabilities, your speed up is less than 10, according to this Amdahl's law. And the same thing happens for the efficiency, right? All right. So before discussing more about this phenomena, let's have a small example in image processing and see how these speed ups are computed. So assume we have an image processing task, and in this task we have an image of n by n size. So n is the image size, and we want to perform two steps. In the first step, we want to multiply the brightness of all pixels by 2. So we want to multiply each pixel of the image by the number 2. And then in the next step, we want to compute the average for all pixels, right? So is that clear? So what is the time complexity of each step if you have n by n image? Give me the time complexity based on the input size.
N to the power of 2.
Okay, this is for the step 1, and what about the step 2? For computing the average
I think
of
the
what?
I think the same.
Yes. So if we implement a sequential program, we need n2 times to compute the first step, and we need another n2 times to compute the second step, right? So if I draw if I visualize it, this is the execution time, and this is the amount of parallelism. So in this case, we don't have any parallelism. So we have to spend n2 times in the first step and n2 times, right, for the second step, and this would be my execution time, right? So a simple sequential program. So the execution time is 2n squared. So let's see about the parallel version. So the question here is how we can parallelize this program. What strategy would you choose for parallelizing such a program? How would you do that? Anyone has any idea? Let me show you the steps again. So try to think about it for a minute, and then you can answer. All right. So any suggestions?
Depending, we can give a number of pixels to each processor
Mm-hmm.
and have it increase those for us. And if we have too many processors, we can also do the average simultaneously.
Okay. So that's kind of correct. We can assume that we have infinite number of processors, right? So we can assume that at least theoretically that we have the number of processors like is n times n, right? So the first strategy for parallelizing this program is to execute the first step in parallel. So we assign each pixel to a processor or to a thread. You can actually do it really on GPUs, but let's do the second step sequentially, right? So we compute the new pixel values in parallel, but we compute the average sequentially. So now let's analyze this program. So what would be the runtime complexity for the first step in this case?
N2, n to the power of 2.
Yes, but we have n processors now, right?
Oh, n processors, then
So it is n squared divided by n, right? Because we are doing things in parallel, okay? And in the second step, we have the same complexity as we had before. So if we visualize it, we see that, so this is the sequential runtime, right? And this is the parallel runtime. So in this case, because we did parallelism, so we are doing a lot of things at the same time. So we have less time complexity, n2 divided by n, if we use n processors, right? And then we have this n2 times for the sequential part. According to Amdahl's law, this sequential part provides a bottleneck for our program, even we parallelize at least in the first step. So let's see what the maximum speed up would be in this case if we use an infinite number of processors, right? So we just need to divide the sequential time 2n squared divided by the parallel time, which is 2n squared for the sequential part, for this part, plus n squared uh, divided by n for the parallel part. And if you take the limit, you see that even if you use an infinite number of processors, your speed up will be limited by 2, which is very low. So in this case, just keep in mind that we fixed the number of the problem size, and we are just uh, evaluating the performance of this algorithm based on the number of processors, right? So we kept the problem size fixed. And if you remember, here we are checking a strong, if I can write it, a strong scalability or a strong scaling. Because in a strong scaling, we just want to know the speed, the maximum speed of our program if we add more processors without changing the problem size. So now let's have another strategy for the parallelism. So in the second strategy, we execute the first step in parallel, similar to what we did before. And the step two of the algorithm also, we want to do it in parallel, right? So we want to, as we did before, we create an array with length n, number of processors, right? To take in the average. We compute the partial sums. Each thread compute a partial sum, partial part of the average, and write it into the corresponding element here, right? And then we sum them up to get the final result, to compute the average, right? So this is how we parallelize a simple averaging problem in this case. So the step one is we use n processors for like a data parallelism, and in step two, we parallelize this. We compute these partial sums in parallel, and then we add them serially. So what would be the time complexity for these steps? First, someone tells me what's the time complexity for the step one. We just talked about that.
N to the power of 2 divided by n.
Yes. What about the second part?
N to the power of 2 divided by n plus n.
Yes. Thank you. So, so in the step one, we have n squared divided by n, and for the step two, we have n squared divided by n to compute the partial sums, and then we need more n operations or more n times to do this serial sum, right? So if we visualize now, we see that for the parallel part, so this is the parallel region now, the parallel portion of our algorithm, and this is the serial portion of our algorithm, right? So we see that still we are kind of uh, we have a serial bottleneck, right? So now let's analyze it in another way. So if you write the speedup equation, you can come up with this. So now someone tells me what happens if I increase the problem size instead of the number of cores. So what happens if n goes to infinity? You just need to compute the limit of this equation, right? In this case, what would be the speedup? You can probably do it as an exercise, but in this case, the speedup will be n if you compute the limit, right? Just divide this term by this term, just to compute the limit. Divide 2 by 2 over n. So then the speedup is n, right? The number of cores. So in this case, you have linear speedup. So what I'm trying to show you in this example is that the problem size, changing the problem size or scaling the problem size really matters when you have parallel algorithms, right? So here I kind of analyze this weak scalability, for weak scaling. So usually in practice, when you want to have a parallel program, you should use larger data, right, to have this weak scaling. So the parallel program is worth implementing usually in practice, like when you are working with these data centers, which have, I don't know, thousands of cores, that your problem is big enough when you're using a large number of processors. And we now want to talk about that. So as I mentioned, the Amdahl's law shows how faster our program can be. And it provides an abstract framework because it doesn't really depend on the software and hardware platforms. And it only relies on the portion of your program that can be run in parallel, but it has some pitfalls. The most important one, the most important one is this one. So unfortunately, in the Amdahl's law, the problem size is fixed and it doesn't consider the problem size to be scaled with the number of cores. So it is only useful when you want to measure the strong scalability, not the weak scalability, right? And according to empirical data, we nowadays using these data centers, we are witnessing a speed ups beyond the Amdahl's law prediction. Because when you have these massive parallel machines, you are using a large problem size to be computed on these parallel machines. And as I showed in that image processing example, you see that if your problem is large enough, then your speed up is going to be substantial compared to what Amdahl's law predicts and strong scalability. And this is encapsulated this variable problem size in another law called Gustafson's law.
Sorry, I have a
Yes,
question about the mean time complexity.
where?
Uh, One slide before this.
Okay.
Yes, here. Uh, you said that the speed up is n, but if the n grows larger than the number of our input,
Hmm.
then it doesn't speed up anything.
Yes, yes. Yeah, here I just consider n to be fixed, right? And we just consider a small n to be much larger than n. Because we now talk about this Gustafson's law, and you will find it out. But we want n, small n, to be scaled as a factor of n, like that,
Mhm. Oh, okay.
right? Okay, so in this law, instead of examining what a parallel program could do relative to a sequential one, as we had before, right? Let me raise this. Okay, so this is quite annoying down here. All right. So in this law, in the Gustafson's law, instead of examining what a parallel program could do relative to a sequential one, so we take it from another route. So we examine a sequential machine. So we check if how a sequential machine would perform if it wants to solve the same problem as the parallel one. So in the Amdahl's law, you have a sequential program, and then you want to know how a parallel program will behave, right? What is the speed up? And in this law, we do it from the other way around, right? So we check, we assume to have a parallel program that takes some time, and we want to know how a sequential program behaves. So now we have kind of different assumptions. The first assumption here is that there exists a parallel program, not a serial program, that requires T time on n processor, right? So this parallel program takes T time if it uses n processors. And then, as before, we consider alpha to be the portion of the total time run in parallel, and 1 minus alpha to be the portion that we do sequentially. And the most important assumption here is this assumption. So in this law, in the Gustafson's law, we assume that the problem size scales with the number of processors. So, and it is a linear scaling. So like the problem size, if it is n, is k times n. So let's see how we can analyze that. So first, I would like to compute the sequential time. So as before, now we should think about it like as a parallel time to be a parallel algorithm to be run on a sequential machine. So here, this portion is run serially, as we had before. And this portion that was in parallel, now it is run in serial. So it is this alpha portion times the time taken by the parallel machine, parallel time, times the number of cores. So this is the sequential time. Then you can compute the speed up, and then you can see, in this case, the speed up is the linear function of n, right? So it means if you increase n, you're basically increasing the speed up as well. And here is the efficiency based on this observation, which is 1 minus alpha divided by n plus alpha. So in this case, if n goes to infinity, this term goes to 0, and the efficiency will be lower bounded by this alpha. So we don't have efficiency smaller than the parallel portion of our algorithm, which is very important and intuitive observation. So we obtain a lower bound for the efficiency using this law if we have infinite number of processors. But in this case also, we ignored the parallel overhead, the communication, and things like that. So as we assume to have the problem size scaling as well, so this framework is suitable for weak scalability evaluation. So here in the left curve, I'm showing the speed up curve for different alpha, different portion of the program that can be run in parallel. And as you can see, for example, if alpha is 95%, so if we can parallelize the 95% of our algorithm, you see that the speed up is linearly increasing. And in the efficiency curve also, you can see a similar thing. So as you increase the number of processors, right, your efficiency is lower bounded by alpha, which is 95% for here. So that's quite interesting. And now we can see that if we scale the problem size with the number of nodes, then we can achieve good speedups. So let's have a quick example about this and compare the Gustafson's prediction with the Amdahl's prediction. Or on the other word, we want to evaluate the strong scalability and the weak scalability. So assume we want to have a matrix multiplication algorithm, right? And in this algorithm, 90% of the work can be done in parallel and 5% of the work can be done sequentially. And the sequential time is 100 seconds, right? So 95 seconds is spent on the matrix multiplication part, which is the parallel part, and 5 seconds is spent on the serial part, which is like memory allocation, the startups and initialization, things like that. So let's see what the prediction is by this Amdahl's law. So the first thing that we need to consider is that to evaluate a strong scalability using Amdahl's law, we should consider the problem size to be fixed, right? So in this case, I fixed the matrix size to be 1000 by 1000. So basically we have 1 million elements, right? So for this fixed matrix size, we spend 100 seconds, right? And now we want to compute the parallel time. So we know that 5% is spent for the serial execution in the parallel execution as well. And then we just need to divide that 95 second by n, the number of cores. So we assume that everything is perfect here. So in this case, if you compute this limit for the maximum speedup, you see that even if you introduce infinite number of processors, your speedup is not larger than 20. So in the best scenario, using this Amdahl's law, your strong scalability only gives you 20 times of speedup, right? Okay. So let's do the same thing with the Gustafson's law or weak scalability. So we consider the same serial problem, but now we increase the problem size with the number of cores. So for example, if I consider 3 different settings, so if we use only 1 core, the problem size would be 1000 by 1000, and the sequential time, as before, is 100 seconds, right? But if we use 16 cores, the problem size I consider to be 4000 by 4000, and if you compute the sequential time for this problem size, then you have 1525 seconds. And if you further increase the problem size to 64 cores, then 8000 by 8000 matrix, then your sequential time is 6080 seconds, right? So now let's compute the parallel time. So in the parallel time, if we use 16 cores, we know that we have, using this 4000 by 4000, the parallel time. So these are not the sequential time. These are the parallel time. I will fix them. So the parallel time is 5 seconds for the serial portion and 95 seconds for the parallel portion, which is this number divided by 16. So the parallel execution will be 100 seconds, as we assumed by the Gustafson's law that the parallel time is fixed, right? So in this case, if you compute the speed up, you have 15.25 times faster speed up, right? And again, if you increase the number of cores, then and if you also increase the number of the matrix elements or the problem size, you have even better speed up, right? So with 64 points, if we increase the problem size, we have 60 speed up. And however, in the Amdahl's law case, if we just care about the strong scalability, in the best case, our speed up is 20. So these are quite important observations when you want to evaluate your parallel algorithms based on strong scalability and weak scalability using this Amdahl's law and Gustafson's law. Okay. So now we have about 10 minutes and I can talk about a general multi-core parallel program design. Now that you know how to measure the performance and how to predict the performance, and you know what kind of parallel machines you are working with, now it's time to talk a little bit about how you design a parallel program. All right. So there are 2 important design objectives when we want to create a parallel program. The first objective is the correctness. So because we have a lot of threads working on the same problem, we have these race conditions, we have synchronization and things like that. So we should make sure that our algorithm or our parallel program produces a correct result. So this is something that we should care about. And the next thing is the performance. So we want to be faster and efficient using the performance metrics that we were talking about. So there are some notes. One important note about parallel program design, which is usually it's not sufficient to turn a sequential program to a parallel program. And it is not actually easy all the time to turn a sequential program to a parallel program. So in most of the scenarios, parallel program design comes from the algorithm design phase. So for a parallel program, in most cases, you need to design a completely new algorithm from scratch. So it's not like that you have a sequential algorithm and you parallelize it uh, using the techniques that we have talked about. So you should be careful that sometimes, especially when it comes to machine learning and optimization, for example, you need to design a new algorithm to enable parallelism and problem decomposition. So for example, when you want to perform a parallel computing on GPUs, they impose many restrictions on the program design. So you should really think what kind of program you are trying to design based on the hardware and the architecture that you are working with. Okay, so let's briefly discuss how we design a parallel program. So you have a problem to solve. This problem, you want to, to, to design a parallel program for solving that. So the first step in the design phase is to decompose this problem that you have into a smaller subproblems that are independent and can be done and can be computed in parallel. And this is the one of the most challenging parts, how you want to decompose a problem into a smaller subproblems that you can compute in parallel. So they should be independent and they should kind of capture the main problem that you want to solve. So this is the first phase, which is the most challenging phase. And then you need to assign each subproblem to a thread or to a process in your parallel machine. So now it's important what kind of parallel machine you are using. So if it is a SIMD machine, you have to assign it differently compared to the case that you have a MIMD machine, right? So now you have a pool of threads, probably you created or like OpenMP has created for you. And then you need to assign each task to be solved by each thread or each process. And then you need to manage the threads because the number of tasks might be more than the number of processes. Then you need to somewhat schedule each task to a corresponding thread or process carefully. And after you did that, you need to do some sort of coordination. So now the tasks are assigned to each thread or process, but they need to coordinate to solve a problem. So they have to do synchronization, they have to do communication, and like coordination or orchestration to solve that problem that you send to them. Because of data dependency, some of these processes they need data from each other, right? So they have to perform this kind of computations and communication. And finally, you have the mapping where you map the actual thread into a real hardware, to a real hardware thread. And this part can be done by the operating system or uh, by the hardware itself. So let's discuss them in more details. So let's talk a little bit about the decomposition. So you can have different decomposition paradigms if you want to decompose a problem. You can have a functional decomposition where you decompose the problem based on different functionalities or tasks. Or you can have data decomposition. Assume you want to process a data set, so you can decompose the data and you can make different partitions out of the data, and then you can kind of process each partition in parallel. So this functional decomposition usually enables task-based parallelism, and this data decomposition enables data parallelism. So this is task parallelism and data parallelism. So these things really depend on the on the problem. So who is responsible for decomposing a program into independent tasks? So because we don't have a automatic decomposition method that receives the problem and automatically decompose it into different tasks. So it is a quite challenging research problem. So because of that, it is the responsibility of the programmer that it is the responsibility of the programmer to decompose the problem into different independent pieces that can be done in parallel. For the decompositions, we can also have some decomposition patterns, which gives you some intuitions about the situations that you can use different kind of decomposition strategies. So let's see how we can use what are these patterns. So as I mentioned, we have a functional decomposition, and this functional decomposition can be divided into linear decomposition and recursive decomposition. In the linear decomposition, you have task parallelism, and the recursive decomposition you have divide and conquer parallelism, which we don't talk about in this lecture, but we talk a little bit about task parallelism. In the next method, you have this domain decomposition. It can be also linear or recursive. In the linear part, you have this data parallel decomposition, and the recursive part, you have recursive data decomposition. We still don't talk about the recursive data decomposition. And finally, you have the data flow decomposition. It can be divided into regular one and irregular one. The regular one uses pipeline parallelism, which we actually don't talk about it, but we talked about that, I think, in the first lecture, if I remember correctly. And we have the irregular decomposition, which you can do using event-based coordination method. We still don't talk about that part as well, but there are different kind of decomposing a parallel, a program, decomposing a problem. So let's have two small examples about the task parallelism and data parallelism. So in the task parallelism, you divide your program into different tasks, and then you run them in parallel. So for example, here is a simple while loop of a kind of video game. You have 4 tasks: read user input, draw a screen, play sound, and strategize the game, right? So for each of these tasks, you can define a task, right? Similar to what we do with OpenMP, and you can run these tasks in parallel. And we just use barrier here to make sure that all threads are on the same position. So this is a simple example of task parallelism or task decomposition. So about the data parallelism, so in this example, I'm showing an image convolution example, right? Where you want to apply a convolution filter to an image, which is quite used in convolutional neural networks. So in this case, I can assign a thread to each of these results of this convolution, right? So I have a 3x3 convolution filter here. Then I'm going to apply it to each part of the image, right? And then I compute the results into another matrix. So each element of this matrix can be assigned to a thread, and that thread can get this data and this filter, right? And it can compute the convolution value and put it here in this matrix. So it's kind of data parallelism because each thread is doing the same operation but using different data. All right, so after the composition, we have the assignment, which is quite simple. We want to assign tasks to the threads or workers, and here the main goal is to achieve a good workload balance and to reduce the communication cost. So in this case, we want to keep the workers or threads to be as busy as possible during the computations without a lot of communications, right? And this can be done by the programmer or by by runtime, like what we had in OpenMP, and also it can be done statically before the program runs or dynamically during the execution. So let me show you an example here. So this is the computing Pi program using OpenMP, but here I am responsible to assign a thread, assign a task to a thread, right? So this is a statical assignment for the thread. So because I am responsible to tell a thread what to do. But in this version, I am using this Pragma OMP parallel for reduction. And it's up to OpenMP how to parallelize this for loop for me. But then this is called automatic assignment, which is done by OpenMP. So it really depends on the program context and on the developer, how you want to do these assignments. Okay. And there are two more steps. I know the class time is over, but just let me finish this part. So we have the coordination phase in which you want to structure the communication, you want the synchronization, and you want to organize your data structures in the memory and how the threads wants to communicate and to work with each other to solve the problem. Again, here you want to reduce the communication and synchronization costs, and you want to use data locality as much as possible. And finally, you have the mapping, which is about mapping the thread or workers to actual hardware execution unit. And this mapping can be done by the operating systems using for the programs like pthreads. So when you are working with pthreads, it's the operating system that maps these threads that you created into your program into the actual execution context in the hardware. And the mapping can also be done by the hardware as well. Like when you write GPU code, the GPU is going to be responsible to map your CUDA threads or CUDA thread blocks into some GPU cores, right? So this is roughly how you would want to design a parallel program as a general, I think. So we're going to have some examples later how for a given problem you can decompose it and you can uh, and you can assign these tasks to a thread and how you can coordinate them, how you can map them into actual hardware. So I try to provide an end-to-end example for that kind of application. Okay, so this is what I wanted to cover in today's lecture. So thank you for your patience. And if you have any questions, you can ask me now. All right, so have a good week and see you next time.